Have you ever looked at a statistic and felt absolutely 100% confident you understood what it meant, only to realize later your intuition was completely backwards? Today, in this explainer, we're taking a mind-bending journey into how our brains actually process probability. We're going to explore one of the most fascinating cognitive traps in all of statistics, Bayesian logic and the illusion of the 95% accuracy rate. Get ready, because the way you look at data is about to change forever.
So let's start with a scenario. Imagine an athlete takes a drug test for doping. Now, this test is claimed to be 95% accurate. The result comes back positive. So, what is the chance that this athlete is actually guilty of doping? Just take a second. Say your answer out loud. If you're like pretty much everyone else, your brain immediately jumped right to 95%. I mean, it feels like common sense, right? Well, hold on to that thought.
Okay, here's how we're going to logically deconstruct this riddle step by step. First, the 95% illusion. Second, crunching the numbers. Third, the false positive paradox. And finally, thinking like Bayes. Part 1. The 95% illusion, setting the trap.
All right, let's out the cold, hard facts directly from our source scenario. First up, we have our base rate. We're going to assume 1 in 50 athletes in our population are truly guilty of doping at any given time. Second, our drug test is claimed to be 95% accurate. Now, practically, this means two very specific things. It correctly catches 95% of the guilty athletes, and it correctly clears 95% of the clean athletes. On paper, 95% sounds incredibly reliable. But to see how it actually behaves, we need to apply it to a whole population.
Let's move to part 2. Crunching the numbers, expected frequencies. To really solve this intuitively, we need to abandon confusing percentages and just look at actual whole numbers of people. Let's build this out. Step 1, we start with a theoretical population of 1,000 athletes. Step 2, based on our 1 in 50 base rate, out of those 1,000, exactly 20 are actually guilty and 980 are completely clean. Step 3, we run those 20 guilty athletes through our 95% accurate test. So 95% of 20 is exactly 19. The test successfully catches 19 doping athletes. 1 manages to slip through, but 19 are caught. So far, so good, right? The test looks fantastic. But we have to look at the other side of the population. Let's look at those 980 completely clean athletes. Remember, the test is 95% accurate for them too, which inherently means it has a 5% error rate. And here is where the math really bites us. 5% of a very large number creates a surprisingly high amount of errors. 5% of 980 clean athletes equals 49 false positives. That's 49 totally innocent people wrongly flagged. And this brilliantly illustrates exactly what happens when you sort those 1,000 athletes out, reconstructing the insights of a frequency tree without getting bogged down in complex math formulas. Look at the top row. Of our 20 doping athletes, 19 get a positive result, and 1 gets a negative result. In the bottom row, of our 980 clean athletes, a massive 931 get the correct negative result, but 49 of them are hit with a false positive. So moving on to part 3, the false positive paradox. It's time for the big reveal. Let's go all the way back to that initial riddle. You took the test, the result is positive. What are the chances you are actually guilty? The answer is 28%. Seriously, let that sink in for a second. A test that is technically 95% accurate only means you have a 28% chance of actually being guilty if you get a positive result. How is that even possible? Well, it's because we expect a total of 68 positive tests in our entire population. That's the 19 true positives plus the 49 false positives. If an athlete tests positive, they are just one of those 68 people. And since only 19 of those 68 are truly guilty, the chance they are actually doping is just 19 divided by 68, which is 28%. Just look at the sheer size of that false positive slice. The source points out a fascinating paradox here. Even though the testing is genuinely 95% accurate, a staggering 72% of all positive test results in this scenario are completely false accusations. While we're using sports to build our intuition here, the core lesson is about the essence of Bayes' theorem itself. It shows us how easily we can be misled when we ignore the underlying reality of a population.
Which brings us to part 4, thinking like Bayes, the reversal. So why does our intuition fail us so spectacularly here? Why did literally almost everyone guess 95% at the very beginning? Well, it comes down to a fundamental misunderstanding of timelines. So the crucial point is we need to understand the difference between how things actually happen and how we learn about them. On the left side, we have the actual timeline of causation. First, the truth exists, right? A person is either guilty or innocent. Then, second, a test is administered. But look over at the right side. This is our knowledge timeline. This is how we actually experience the world. First, we get a test result, and second, we try to use that result to figure out the underlying truth. The source material notes that Bayes' theorem essentially restructures the data to respect this temporal order of how we come to know things, completely reversing the timeline of causation.
And because our brains just don't naturally reverse that timeline, we fall into a massive cognitive trap. As the source directly states, it is terribly easy to confuse the probability of testing positive, given that you are guilty, which is 95%, with the entirely different probability of actually being guilty, given that you tested positive, which is only 28%. Our brains casually swap the two halves of the sentence, basically assuming they mean the exact same thing. But as we've seen, they absolutely do not.
In fact, this reversal is so central to the whole concept that up until the 1950s, Bayesian thinking was simply known as inverse probability. It's literally the mathematical equivalent of being a detective. You arrive at the scene of the crime, which is the positive test result, and you have to work backward, inversely, to figure out what actually caused it. Was it the 19 true positives or the 49 false positives?
To wrap up this explainer, I want to leave you with a powerful final thought straight from the text that perfectly captures why this logic is absolutely crucial. This is a special case of a rather unintuitive truth. When the thing you are looking for is rare, then even if a screening test appears to be accurate, the majority of your identifications may be wrong. When you are looking for a needle in a haystack, then even if you have good eyesight, most of what looks like needles will be hay. So if a 95% accurate test can be this catastrophically wrong when looking for rare events, you really have to ask yourself, what other absolute certainties in your life are actually just statistical illusions?